Hey, this is Chris Plush from CG Masters, and this is a free lecture from our upcoming course, the Blender Encyclopedia. This is an all-in-one type course with more than 50 hours of training for the latest version of Blender, including tutorials for every single shader node, like this comprehensive look into the Principled node and the science behind physically based rendering. So check the video description for more info on the course, and I hope you like this tutorial. In this lecture, we'll learn about the Principled node, which is an all-in-one type node that can be used to create realistic materials. In order to understand this node and shader creation better, we'll also be going over some of the basics behind PBR, or physically based rendering, which is simply shading and rendering that's based on accurate physics. So we're going to learn some of the science behind this node. So the Principled node was first created at Disney, focusing on realism, simple settings, and some artistic freedom. They developed the node with these principles in mind, and that's why it's called Principled. For example, you'll notice that almost all of these settings are in a simple to use 0 to 1 range. And this 0 to 1 range gives the material a result that's plausible in reality. However, you also have the freedom to type in values beyond the realistic 0 to 1 range. For example, clear coat only goes up to 1, but I can type in 20 for a stronger effect. So keep that in mind if you feel the need to stylize your results more. Alright, so let's dive into everything now. Now it's useful to know how a physically accurate material is actually built. So that's how we're going to start things off. And we'll start with non-metal materials, also called dielectric materials. Now, dielectric materials like marble, for example, both reflect and refract light. Some rays reflect right off the surface, producing more mirror-like reflections, which we'll refer to as specular reflection. But some rays transmit through the material a little, and we'll call those rays refracted rays. Now, these rays scatter underneath the surface a little. Some light gets absorbed, but the rest bounces back outside the material in slightly different locations and random directions. So these refracted rays do not produce mirror-like reflections. Now, in Blender, we recreate this complexity in two layers. First, we have a diffuse layer, which we can see by turning off the specular reflections real quick. So this here is the diffuse layer, and it simulates refracted rays getting scattered or diffused under the surface. You'll notice it's blue too, which we chose as our base color here. Remember that some light gets absorbed, so in this case, this material is absorbing red and green light, and only blue light is bouncing back outside the material. Now on top of this diffuse layer, we add on a specular layer. So let me increase the specular value back up to 0.5. Now this top layer simulates surface reflection and produces more mirror-like reflections. And that's actually it. We now have a physically accurate dielectric material. Now the specular layer is added on top of the diffuse layer realistically using something called Fresnel. This is the effect where specular reflections are stronger on the edge of something like a sphere than they are in the middle. The angle a light ray hits a surface is called the angle of incidence. If a ray hits the surface at a low angle of incidence, or more straight on, it's more likely to penetrate and refract, producing more diffuse reflection. And when a light ray hits the surface at a higher angle of incidence, or more parallel, it's more likely to simply bounce right off the surface, producing more specular reflection. Which is why there's more specular reflection on the edges of the sphere and less in the middle. So Fresnel is simply how much light gets reflected or refracted at any given angle. Now, Fresnel is different for all materials. Every material has something called an index of refraction, or IOR, which basically defines how light interacts with the material. This is used in the Fresnel equations to determine how much light is reflected or refracted at different angles. And we can use the specular slider over here to control the IOR value. And as you can see, the higher the IOR value, the more specular reflection we see, especially at lower angles of incidence, like the center of the sphere here where light hits it straight on. And now as we lower the IOR value, in fact, I'll put it really low to 0.03, you can see there's less specular reflection in the center of the sphere. At a low IOR, the angle of incidence has to be much higher before light is more likely to bounce off and give us a specular reflection, which is why the very edges of the sphere still have an almost mirror-like reflection. Now this graphic here shows spheres with different specular values. The white represents the amount of specular reflection at each value. So you can see the specular slider isn't just a strength slider for reflection, which it might seem like at first. It actually produces specular reflection based on the IOR and the angle light hits the surface. And at all values except 0, specular reflection approaches 100% as the angle of incidence approaches 90 degrees, or parallel to the surface, which is why the rims of all the spheres, no matter the IOR, are bright white still. Now if you want to use real IOR values here in order to get a physically accurate material, you can find a huge list of IOR values for all different materials at pixelandpoly.com/ior.html. Now, one problem is that you can't just input the IOR value into the specular field here, because like I mentioned, a focus of the principled node was usability, so all these sliders are in a 0 to 1 range. Now, most IOR values are actually above 1 though, so a formula is used to convert IOR values to get a 0 to 1 range. So here's the formula used to get a specular value from an IOR value. Now, if you wanted to automate the IOR conversion using nodes, you can set up a couple of nodes that I already have here. So let me pull these over a little bit. So this chain of nodes starts with the value input node on the left, and this value runs through some math nodes that represent the formula I just showed you. So now we can input the IOR value here. So for example, I'll type in 1.635, which is the IOR for asphalt, and then it uses these math nodes to automatically convert it to a 0 to 1 value. And then we'll just plug this chain into the specular field right there, and now it's using the converted IOR value as our specular value. And here's that node setup again if you want to copy it. Alright, now let me delete all of these. Let's go back to our principled node here, and I'll reset this back to 0.5. Now for dielectric materials, the most common IOR is around 1.5, which converts to a 0.5 specular value. And that's why 0.5 is the default value for the specular field here, because that's what it should be most of the time. So a lot of the time when creating dielectric materials, you won't even have to change this if you're going for realism. But of course you can if you simply want to tweak the look of something. Alright, so let's move on to specular tint real quick. This is purely an artistic addition to the node and not realistic. Only metallic materials tint reflections in real life, but you can use this slider on dielectric materials to tint their reflection using the base color. So you can see the reflections are now more blue. So that's what that does. And alright, that's your basic dielectric material construction layer by layer. You have a diffuse base layer and then a specular layer added on top of that using Fresnel. Now let's go over how a metal material is built. Metals are actually entirely specular. They don't have a diffuse layer like dielectrics do. Just like with dielectric materials though, metal both reflects and refracts light. But in the case of metal, any light that refracts gets absorbed and does not bounce back out, so there is no diffuse reflection. So to create a metal material, we have this metallic slider right here, and this goes from fully diffuse at 0 to fully specular or metallic at 1. So now the material is entirely specular and has no diffuse. The material is now metal. Now you can see how the specular reflections are also tinted by the base color. Colored reflections are a property of metals due to how metal interacts with different wavelengths of light, or colors in this case. So since we're working with a blue metal here, let's see how it gets its blue reflections. So we can visualize a ray of white light as having a red, green, and blue channel. When this light hits the surface of our metal, the red and green channels are more likely to refract and get absorbed, and the blue channel is more likely to reflect off the surface. So this produces a blue reflection in the end. And depending on the type of metal, it'll refract or reflect different colors of light, giving it different specular reflection color like gold for example. Now if we zoom into the edge of the sphere here, you'll notice that this specular slider is actually creating a Fresnel effect. This is producing a white reflection on the rim of the sphere instead of a blue reflection. And this is actually important because metal has Fresnel as well. Just like with dielectric materials, at higher angles of incidence, all colors of light are more likely to bounce off the surface instead of getting refracted. So on the edges of the sphere, we ended up with white reflections instead of colored. And this is important even for gray metals too. For example, if I change the base color here down to 0.4, take a look at the rim of the sphere there as I change the specular value. You can see it gets darker at 0 and brighter at 1. So the specular value in the case of gray metals will simply produce brighter reflections at higher angles. And let me switch that back to blue. Now that was all a simplified explanation. Metal is actually really complex when it comes to reflectance, but we won't go into any more detail in this lecture. Just know that the specular value in this node doesn't really take this complexity into account. It's actually more for dielectric materials, but you can still use it for a simpler Fresnel effect for metal. So what I would do is just adjust the specular value to whatever looks realistic, and sometimes that might be really low values or even 0. And now some extra notes on the metallic slider. This should either be set to 0 for diffuse or 1 for metallic. Nothing in nature is in between, but of course you can set it to something in between if you just wanted to stylize the final look. Also, if you're texturing an object where some parts are metal and some are dielectric, like a piece of wood with some metal screws in it for example, you can plug a black and white metallic map into the metallic input, and that'll define which parts are which. For example, if I add in a checker texture and I plug that factor value in as the metallic map, you can see that some of these squares are diffuse and some are metal. The squares that are black have a value of 0, so they'll be diffuse, and the squares that are white have a value of 1, so they're going to be metal. Alright, so the next value we're going to go over is roughness down here, and this is how physically smooth or physically rough the surface of an object is. If a surface is perfectly smooth and has a roughness of 0, you're going to get sharp reflections, and if it's rough and has a higher roughness value, you're going to get more blurry reflections because the light rays get scattered more when they bounce off the surface. Now, this doesn't just affect the specular reflection, this will affect your diffuse layer as well. For example, I'll turn the specular layer off so we see just the diffuse layer, and let's zoom in to the area down here, it might be more noticeable. I'll turn roughness down to 0, and then watch it closely as I turn roughness up. You can see there's definitely a change there. And it is subtle, but the roughness value affects the base diffuse layer too by scattering the light even more. So in general, the roughness value just scatters all reflections more. Alright, let me reset specular back to 0.5 so we have our basic dielectric material again. Now, just a quick note on dielectric materials. If you have a really rough surface, you might be tempted to turn specular all the way down to 0 so you just have a diffuse layer. A more realistic way to approach this, though, is to keep specular where it's at and increase the roughness instead. Since, like we learned about dielectric materials, they have both a diffuse layer and a specular layer, so turning the specular layer off completely wouldn't be realistic. And one more note about the roughness value. At the very top here, we have a menu for distribution, which basically defines how the reflection roughness is calculated. Basically, GGX is less physically accurate than multi-scattered GGX, but it renders faster. There's usually not a major difference between the two, so the default GGX is typically fine. And you can see more about these distribution models in the glossy node lecture. Alright, now let me switch over to example 2, and we're going to go over subsurface scattering now. Subsurface scattering can be used for things like wax and skin, where light that enters the material is scattered significantly, creating a softening effect and even allowing light to pass straight through the material if it's thin enough. Now, this happens when light penetrates a material, then the rays scatter underneath the surface before exiting the material at different locations and in random directions. If that sounds familiar to you, it's because this is actually the same as the diffuse layer. The diffuse layer simulates microscopic scattering though, meaning the refractive rays don't travel a significant distance, so it won't noticeably spread out the light, and instead just produces a very scattered reflection. With significant subsurface scattering though, refracted rays travel a larger distance through the material before exiting, spreading out the light, which is why this can have such a strong softening effect on materials. And because light travels further in the material, in some cases it might travel entirely through the material to the other side if it's thin enough, creating an interesting effect for things like backlit ears and lit candles. So this is a very important effect for a lot of different materials. So how do we use it? Well, the subsurface slider right here increases the scattering effect, and this goes from regular diffuse at 0 to full scattering at 1. So let's try putting this at 0.15. And there we go. So increasing the subsurface scattering a little diffuses the light underneath the surface more, spreading it out and creating a much softer look. And like I mentioned, because this increases the amount light travels underneath the surface, in thinner areas like the ear right here, the light coming from behind the ear is actually shining right through it, creating this extra lighting. Now we can give the subsurface scattering layer its own surface color as well, using the subsurface color option right here. For example, if I made that blue, and I increase subsurface a little bit, you can see it's like we're mixing the peach diffuse layer with a blue subsurface layer, so it results in a more purplish color like that. And let me undo that. In the case of something like skin though, and most things, we'd probably want to keep the same color as the diffuse layer. So let me press Ctrl and C over the base color, and I'll press Ctrl and V over the subsurface color. That way we're not changing the material's main color when we increase the subsurface scattering. We're just changing how much light gets scattered. And next let's go over the subsurface radius, which is a very important control that defines how far each color of light will travel underneath the skin. Now if I click on this, you can see it's separated into red, green, and blue channels. And by default, these values are set for something like human skin, where red light will travel deeper. So red, you can see, is up very high, and the other colors are lower, which means they don't travel through the material quite as far. And that's why the color coming through thinner areas like the ear here is reddish, because we have red light being able to travel farther in this material, so it traveled right on through the ear, illuminating the other side. If we instead switch these values and we made red light travel less far and blue light travel the farthest, then you can see it's the blue light that's coming through the ear now. And let me reset these. And actually that's all there is to it for these options, and you can learn more about all of this in the subsurface scattering node lecture as well. Alright, now next up is the anisotropic options right here, and for that we'll switch over to example 3a. Now the anisotropic options here are used to simulate the reflection effect you'd see on something like brushed metal, like on the bottom of a steel pot for example. When you have ridges or scratches all traveling in the same direction, they reflect the environment in such a way that seems to stretch it out based on the scratch directions. So on the bottom of a steel pot, for example, you might have scratches going around in a circle like this, and they're going to stretch the reflections out radially, starting from the center, pulling outwards to the rim. And any scratches going horizontal like this are going to stretch the reflections out vertically, like you can see right here. So that's the effect that the anisotropic option tries to simulate. Now in this example here, I actually modeled all of these ridges, and I modeled them pretty large too, just so that you can see them and understand the effect I'm talking about. The anisotropic option though would be most useful for more microscopic scratches or ridges though, like on brushed metal. So for that, let's head over to example 3b, where I have another cylinder here, but this one does not have any ridges modeled in it. So we're going to use the anisotropic option to simulate that effect on this. Now to recreate that effect on this cylinder, let's turn anisotropic all the way up to 1 first. Now it doesn't actually do anything unless we also increase the roughness value here, which makes sense because if the effect is based on there being scratches or ridges on the surface, it's not a smooth surface. So let me turn that up a little bit, and you can see the effect taking shape. And you can actually rotate how it stretches the reflections using the anisotropic rotation value here. Now it's important to note that the reflections are stretched out based on the center of the geometry. So right now the center of the cylinder is being used as the center of the effect. But if I go into edit mode, make sure everything's selected, and I press Shift and D to duplicate this and move it, you can see it's now using the center of both cylinders as the center of the effect, which is why the center is around right there. So definitely keep that in mind. And now let me switch over to example 3c, where I have a cube here that has the same exact shader. Now also keep in mind that the direction of stretching is also based on the object's axis. Right now this object's z-axis is pointing straight up by default, so we get radial stretching on top of this cube. But we can also change that direction using the tangent input node. Let me press Shift and A, and from the input menu I'll add in tangent. And I'll connect tangent output to the tangent input there, and now we can use these axis options here to change which axis the effect is created on. And that does it for that. So now let's move on to the sheen options here, which add some additional soft reflection on the edges of your model, which is especially useful for cloth. So let me switch over to example 4 for that. And let me switch to material preview too so things render a little faster. Now let's try turning the sheen value up to 1. And in fact, let's crank it up to 5 so we can really see the effect. So you can see this basically added some rim lighting. And this is a pretty useful effect for adding a soft velvety look to materials like cloth. It seems to simulate the fuzziness of a cloth surface, which catches the light more around the edges. And the sheen tint option here will simply color the effect based on the base color. And that's it. And now let's move on to the clear coat options here, which add an extra specular layer on top of your shader. And for that, we'll switch over to example 5. So let's say we're creating car paint. First we add in the base paint, which is a metallic paint, so I have set metallic up to 1, and this has a higher roughness value to give the surface a diffused look to it, so I have roughness set to 0.5. The problem is, adding higher roughness means that we don't have any sharp reflections, as you can see. That's where we can turn up clear coat, so let me turn this up to 1. And there we go. This added another layer of specular reflection for us. So it's like this was another layer of clear coat paint on top of our metallic paint. And we can control the roughness of just this specular layer, just this clear coat layer, by using the clear coat roughness value right here. Now this clear coat layer can also have its own normals by plugging in normal data into the clear coat normal input down here. Any normal info plugged into that input will only affect the clear coat layer and not the layers underneath, which is really useful if you wanted to simulate something like orange peel, which is the waviness that happens on just the clear coating of car paint. So for example, I have a noise texture down here that's already ready to plug into that input to simulate that orange peel effect. So let me plug that in. And there you go. You can see how the clear coat layer is very wavy now. In fact, a little bit too much. So I'll turn that down to maybe 0.02. Still a little too much, but who cares? Just for demonstration. And that bump map right there is only affecting the clear coat normal layer. It's not affecting the layers underneath. So the clear coat normals are totally independent from the regular normals. In fact, if we plug this into the regular normal input instead, and we crank the strength up, you can see only the bottom layers are affected by the bump map now. But our clear coat layer is not affected by that, and it instead acts like a perfectly smooth layer of polish on top. So this can be used to create some complex layered materials like that, which is very, very cool. All right, that's it for that. So let me switch over to example 6 now, where I have this little cup right here. And I'll select that. And now we're going to go over the IOR and transmission values down here. And these are for creating transparent materials like glass. Glass, for example, like every other material, both reflects and refracts light. For transmissive materials like glass, though, when light refracts, it doesn't bounce back out like it does for a dielectric material. It instead goes right through the material. And because light travels at different speeds through different mediums, it'll bend when it both enters and exits something like glass, creating a distortion effect. Now for this example, we're going to render this in cycles, since that handles refraction more accurately. And in order to create a transmissive material, we simply need to turn transmission up to 1. And now we have glass. Now the IOR value here determines how much light bends as it travels through the material. It also determines the amount of Fresnel. So an IOR of 1.01, for example, will have very little bending effect and very little specular reflection, especially at lower angles of incidence. But an IOR of 2 will bend the light a lot more and also increase the amount of specular reflection. Now you might remember that the specular field up here is also basically an IOR field. This field is specifically for non-transmissive materials though, and it only handles Fresnel. It's completely ignored when a material has a transmission value of 1. So in that case, only the IOR value down here is taken into account, and the specular field has no effect. You can see it's the same at 0 as it is at 200. It has no effect whatsoever because our material has full transmission. So if you're working with a fully transmissive material, you only have to worry about the IOR field right here. And again, you can find a material's IOR at pixelandpoly.com/ior.html. Also make a note that you don't need to convert the IOR value for this field like you do with the specular field. For this field, you just plug the IOR value in as is, and it works right. All right, let me align the view to where I'm looking in the glass, and I've got a strong specular reflection on the outside of the glass like this. Now let's go over the transmission roughness value here. What this does is it scatters light that transmits through the material. So it's an internal roughness value basically. For example, if I turn that up to 0.2, you can see the light scatters as it goes through the material, making it look blurry. But note that the specular reflections on the surface are still sharp, because this value only affects light that goes through the material, so it doesn't affect specular reflection. And let me turn that back to 0. Now, as a side note, this transmission roughness is different than the other roughness value up here. Transmission roughness determines the internal roughness, whereas the roughness value up here determines the roughness of the surface. So if I turn this up to 0.2, for example, this will scatter all the light hitting the material, which contributes to everything looking blurry, including the specular reflection. But you can use both values together to make a more complex material. Like, let's say we wanted a slightly rough surface, so I'll turn that down to 0.1. And I also want the light scattered more as it goes through the glass, so I'll turn transmission roughness up to 0.3. And there you go. So there's a lot of combinations possible with this node. All right, so we're done with that. Let's switch over to example 7 now, and we're going to go over the emission option. So let me select the platform here. Now the emission value right here simply makes the material emit light. If, for example, we made this platform emit a red light, you can see it's emitting light into the scene, so it's adding extra illumination to the monkey head and anything that's around it. And you can turn these values up above 1 as well. For example, if I turn red up to 15, now it's really blasting some red light into the scene. And you can plug an emission map into this input as well. Like for example, I have an image node over here that already has an emission map, and let me press Control, Shift, and left click on that to preview it. So you can see most of the platform is black, but I have this ring as white and this ring as white. And those are the areas that I want to emit that red light. Now let's change those colors by running this through a color ramp. So I'll press Shift and A, and from the converter menu, I'll add in a color ramp and plug it in right there. And let's change the white value here to red. And I'm going to do the same thing. I'm going to crank that up to 15 for the red value. And let's plug the principled node back in to the material output, and I'll plug this color value into the emission value of the principled node, just like that. And there we go. So now only areas meant to emit light are emitting that red light. And that's it. So this is a newer feature to the principled node, and it prevents the need for mixing in a separate emission node, which is what we had to do before when we had textures that included some elements that emitted light. All right, now let me switch over to example 8, where I have this leaf texture on a plane. And now we're going to go over the alpha option down here. And this is another new option added to the principled node. And the alpha option simply makes objects see-through. For example, if I decrease the alpha here, you can see it becomes more and more transparent. And it's not like glass or anything like that. This doesn't refract light, it just makes the object more invisible. And this is useful for anything that would use an alpha map especially, like this leaf for example. Right now I just have the leaf's color map plugged into the base color of the principled node, but we still need to use an alpha map to make the area around the leaf invisible. And for that, I'll duplicate this image texture node here. I'll load in the leaf's alpha map, and let's get a preview of this. So the black areas have a value of 0, so they're going to have alpha value of 0, which means they'll be transparent, and the white areas have a value of 1, so they'll remain opaque. So let me plug the principled node back into the material output, and we'll plug the alpha color into the alpha input right there, and there we go. So now only the white areas of the alpha map are left visible. So this new option prevents us from needing to mix in a separate transparency node, which is what we had to do before. So the principled node is really more useful than it ever was. And that's actually going to do it for all the options in this node. But I do have some final thoughts that you might find useful. First, this does not replace all other shader nodes. It's still useful to use the other shader nodes in certain circumstances, but it's often very handy and convenient to base your material off of a principled shader node, especially if you're striving for realism. And second, I wanted to clarify something about the specular slider here. You may have heard of things like specular workflows or specular highlights. Those things are not the same here. The word specular in this case is used to mean regular reflections, and this slider is based on IOR values. So this field is not compatible with specular maps and specular workflows. Those are different things, and a specular map plugged into this slot is not going to work the way you think. Alright, and that's actually going to do it for everything, so I hope you learned a lot in this lecture, and I'll see you in the next one.